Hey, pre-AP, pre-calc students. Today we're going to talk about the factor and remainder theorems. And so to do that, let's start with the factor theorem. The factor theorem says if a is a zero of a function, then the factor x minus a is going to be the factor of f of x. Put another way, when f of x is divided by the factor x minus a, then the remainder is 0. Okay? So what we're going to do is we're going to look at this idea and see what we can establish here. So, is 2x plus 1 a factor of this polynomial? Show and explain your work. Okay, so we're dividing here. So what we want to do is we want to see if 2x plus 1, the 0 there is going to be negative 1/2. I want to see if that goes into, let's see, 2, 3, negative 11, negative 6. Okay? I want to see what happens with synthetic division. Bring down your 2. 2 times 1/2 is negative 1. 2 times negative 1/2 is negative 1. 3 minus 1 is 2. 2 times negative 1/2, negative 1. That gives me negative 12 when I add those. And negative half of negative 12 is positive 6. And we get a remainder of 0. So my resulting polynomial is 2x squared plus 2x minus 12. And so now when I look at this, I can say that, oh, it says what are all the factors? Or no, it doesn't. It just says it's 2x plus 1. Yes, because the remainder is 0. The graphical interpretation of the result of this work means that x equals negative 1/2 is an x-intercept of the polynomial. Let me put that, of g of x. Okay, let's try another one. Let me switch colors here. Is x plus 2 a factor of this polynomial? So again, we're going to put negative 2 on the outside. And looking at my polynomial, I have 2, negative 1, 3, and negative 8. Bring down the 2. 2 times negative 2 is negative 4. I'm just doing this real quick. Alright, when we look here, we can see, so no, x plus 2 is not a factor. The remainder is not 0. So this means that negative 2, I wrote that wrong, sorry, x equals negative 2 is not an x-intercept of the function f of x. Okay? Alright, consider the function f of x equals x cubed minus 13x plus 12. Okay, so first we're going to divide f of x by x minus 3. So that means I'm going to have 3 on the outside. Now please note here that there is no x squared term, so we need to insert that in. So we're going to write our coefficients of 1, 0, negative 13, and 12. Bringing down the 1, 1 times 3 is 3. Eek. That is just looking awful. I don't know what's going on here. There we go. 3 times 3 is 9. Negative 13 plus 9 is negative 4. And negative 4 times 3 is negative 12. Oh, we get a remainder of 0. Okay, so remainder is 0. So x minus 3 is a factor of f of x. For the next one, we're going to divide by x minus 1, so 1 goes on the outside. And we're going to use those same coefficients that we had before. Bring down to 1. And when we look here, we can see we have another remainder of 0. So x minus 1 is a factor of f of x. Alright, now let's do x plus 4. So we're going to put a negative 4 on the outside, and we're going to use those same coefficients from the polynomial inside. And we can see we have a remainder of 0. So that means x plus 4 is a factor of f of x. So based on the work that we did in number 3 here, what are the zeros of f of x? So since the factors are x minus 3, x minus 1, x plus 4, the zeros are x equals 3, x equals 1, and x equals negative 4, which are just precisely those numbers that are on the outside of the division symbols. All right, so that's how we use the factor theorem. So what we're going to do now is we're going to extend that a little bit. So if x minus 1 is a factor to this function g of x equals 2x cubed minus 3x squared minus 2x plus 3, what are the other two factors of g? And rewrite g of x in completely factored form. So I'm going to stick the 1 on the outside, and I'm going to write the coefficients of g of x inside. There are no terms missing, so I can just go right into it. 2 times 1 is 2. All right, looking here, when I use x minus 1, x minus 1 is a factor because we got a remainder of 0. So now this becomes 2x squared minus x minus 3. We can now factor this. So what multiplies to negative 6 and adds to negative 1? Well, that's going to be negative 3 and positive 2. But we have an a term of 2, so we're going to divide these by 2. And so that'll factor as, when I look at that, negative 3 over 2, that becomes 2x minus 3. And then the 2 divided by 2 is 1, so x plus 1. So that means we're going to have, oh wait, they don't want the zeros, they just want the factors. Okay. And then of course we know x minus 1 is also a factor. So here is the completely factored form for g of x. I should probably make note that that's g of x equals that. Here, let me just draw this again. Okay, there we go. Let's try another one, do a different color here. If x plus 2 is a factor of this, what are the zeros? Okay, so we're going to put negative 2 on the outside, and let's see, we have 3, 2, 1, 0. All terms are accounted for. Bring down your 2. And it looks like we get 2x squared minus x minus 6. So now I'm going to factor that. So AC is negative 12 and RB is negative 1. So we're using negative 4 and positive 3. But we're dividing them by the a term of 2. So we're going to have x minus 2 and 2x plus 3. And let's, of course, not forget about x plus 2. So now, what are the zeros? Well, x equals 2, x equals negative 3 halves, and x equals negative 2. Those will be your zeros. All right, this next one goes a little deeper. So now it's asking you, okay, what value of k is the factor x minus 2 a factor to this polynomial? So we know that x minus 2 is the factor, so we put positive 2 on the outside. 6, negative 19, k, and 6. Bring down that 6. 6 times 2 is 12. Negative 19 plus 12 is negative 7. Negative 7 times 2 is 14. So I'm going to have this factor will be k plus 14. And when I multiply that by 2, I'm going to get 2k plus 28. So then we get 2k plus 28 plus 6, which makes 2k plus 34. We want that remainder to be 0 because it asks for when it's a factor. So a factor means that the remainder must be 0. So now let's solve that for k. We get 2k equals negative 34, which means k has to be negative 17. Okay. All right, let's try another one. For this one, x plus 3 is the factor, so we're going to have negative 3 on the outside. Polynomial, negative 3, k, negative 23, negative 6. Bring down your negative 3. Negative 3 times negative 3 is positive 9, so this gives me k plus 9. Multiply that by negative 3, and you get negative 3k minus 27, which gives us negative 3k minus 50. Okay, negative 3k minus 50 times negative 3 is going to give me 9k. So I'm distributing here, plus 150. So I end up with 9k plus 144. And again, we want it to be a factor, so we have to make the remainder 0. Solving this out, we get 9k equals negative 144. Divide that by 9, and we get negative 16. That's what k would have been. Okay, next one here, x plus 1, so we use minus 1. And it's asking if it's a factor. So we're going to check and see. Bring down your negative 3. And the remainder is 0, so yes. Oh wait, but it says how many times. Okay, so this gives me negative 3x cubed minus 4x squared plus x plus 2. Now, it's asking how many times is that a factor. So what we want to do now is use that polynomial, and we're going to see if negative 1 can go into that again. So let's see if it does. Drop down your negative 3. Okay, it looks like it works a second time. So now let's see if negative 1 is a factor to those numbers again. And look at that, it works again. So negative 1 is x plus 1 is a factor 3 times. And that's because we did 3 synthetic divisions and we were able to get this to work out. Okay, so that's the factor theorem. Then we get to the remainder theorem. The remainder theorem says if you divide a polynomial p of x by x minus a, then the value of p of a is the remainder of p of x when divided by x minus a. All right, so let's look at an example. So let's say I wanted to find the value of f of 4 in this function. Well, you could just plug it in and chug it out, as you can see here. Plugging and chugging, plugging in 4 for x's, we get 64 minus 28 minus 6. And if we do that, that gives us 30. But we can also check it with synthetic division. Okay, so f of 4 means that we're going to use 4 as our number on the outside. Notice they're giving us the 0, the potential 0. And so we're just going to be using 4. I will notice also they give you the x minus 4 as the factor, so the 0 would go on the outside. We're missing the x squared term, so we have to consider that there. And let's see what happens. 1 times 4 is 4. 4 times 4 is 16. 9 times 4 is 36, and negative 36 plus negative 6 plus 36 is 30. Those are the same. Okay, so looking at that, you might think, why in the world did I even have to use the remainder theorem? I could have just plugged and chugged and get the same thing, and it might have been quicker. Well, yeah, in this case it was, but let's say we have this crazy polynomial, such as this one. Well, if we plug and chug here, we're going to have to use a calculator, and we're going to be getting some big numbers. So if I look here, 7 to the power of 6. That term alone is 117,649. If I take 7 to the 5th and then multiply that by 4, we're going to get 67,228. And if we do 7 to the 4th and multiply that by 19, we get minus 45,619. That's not fun, and I'm not going to keep doing that because there's a lot of room for mistakes. So instead, we are going to use the remainder theorem. Now, they give you the function value of 7, so we don't have to put the opposite out here because they're just saying, okay, what is f of 7? I'm going to look at these coefficients here, and I'm just going to write them down. So we have 1, negative 4, negative 19. We're missing the 0x cubed, so we have to put a 0 in there. And then negative 90. Oops, I didn't make this small enough. Negative 55 and 9. Drop down your 7. 7 times 7 is 49. And yeah, these numbers might get a little big, but not nearly like what we had. So I'm just trucking right along here. Okay, so these are getting a little bigger, but not as bad. Sorry, let me fix that. I'm just using my calculator at this point. Okay, this number is 100,898. Subtract 55 from that, we're going to get 100,843. Multiply that by 7, that's going to give me, that'll give me 705,901. And if I add 9 to that, we get 705,910. A lot of grossness going on there, right? This is why we want to have the remainder theorem. So, yeah, that one was gross. I get it. Okay, so let's apply these ideas, okay? All right, last piece here. So for this one, it says, if this is our polynomial, what's the remainder when f of x is divided by x minus 2? So we're going to put 2 on the outside. Now let's see, we have a 4, a 5. We're missing the x cubed, x squared, and x terms, so we need a lot of zeros there, and then 1 at the end. looks like 209. So f of 2 equals 209. Okay. Let's try another one here. So we want to divide this by x plus 10. So we're going to put negative 10 on the outside. 5, negative 3, negative 1. And this would mean that f of negative 10 equals 529. Okay. These next ones ask you to find the value of k that makes these true. So let's see. So it's going to be a lot like what we did before. So we're dividing by x plus 10. So we put negative 10 on the outside. Write our coefficients here. We know this remainder needs to be 67. So we'll figure that out momentarily. So we know that k plus 80 must equal 67 to get that remainder there. So minus 80, k has to be negative 13. Okay? All right, last one here. Let's try this one. So we're dividing by x minus 4, so we put 4 on the outside. Write your coefficients. All right, k plus 8 multiplied by 4 gives me 4k plus 32. So 4k plus 32 plus 19 is going to be 51. And we need that to equal 35. Okay? All right, so solving that out, we get 4k equals, we're going to do 35 minus 51, which is negative 16. So k is negative 4. Alrighty, that should get you understanding the factor and remainder theorems. So now you'll get a chance to do some practice.